Go.
Warning, it's been 3 years now and we're still untrained professionals. This experiment contains overhead weights and much precaution should be used. There is potential for broken fingers, toes, and depending on your IQ, a mild concussion, even tuberculosis.
Throughout our experiments with the Rubik's Cube, we realized that some of the flames were rising a little bit higher than normal. And when it was all said and done, I think we all have a minor aptitude for the force. This is our second experiment of us levitating weights. I hope you all enjoy it.
No strings!
At this point, you may be wondering, why is Hector laying on the floor? I'll tell you why. We have faith in our physics experiments.
As you may have noticed, we have two weights suspended in thin air by a thin fishing line. One weight we're going to pull with a sudden, hard jerk, while the other weight we're going to pull with a slow force downwards. Notice the two effects that these weights have. Now time for our first try. We're going to take this 2.5 pound weight here, pull it with a hard, sudden jerk, and what y'all may think is going to happen is this weight is going to be sent crashing into Hector's sternum. But what is actually going to happen is different. Now watch. Notice that the weight is still there even though Stephen applied a hard, sudden jerk to it.
At this point, you must be thinking, Hector must have a large amount of courage.
Since we care about our physicists, we're going to have Hector move out of the way as Stephen comes and pulls the second weight with a slow, steady motion that will come crashing to the ground. That almost broke my toe.
Because of the large amount of unnecessary attention problems we did in Mr. Alanis's Physics B class, my group and I have a certain aptitude for these problems. And the explanation for our experiment is as follows. In the first situation, you may have noticed that the weight did not fall and hit Hector on the chest. This is because of the quick sudden jerk that we applied to it. This sudden jerk, because it was applied over a small period of time, resulted in a very small amount of acceleration. And by the Newton's second equation, F equals ma, this small acceleration also resulted in a small force. Because there was a very small force, this small force added to the weight of the object did not change the tension in the upper string by very much. Although it didn't change the tension in the upper string a lot, this force resulted in enough tension in the lower string to break it off before it broke the upper string.
And now for the explanation of the second part of our experiment. The force that we applied to the weight was delivered over a longer period of time, which caused a greater acceleration, and as modeled by by Newton's second equation.
Really, Matt?
F is equal
Matt,
to
it's already a messed up film. We've been doing this over 300 times. Get over here. Let's go. Get over here.
Please, guys.
Okay, I'll get it right. I'll get it right.
We've done your scene 384 times. When are you going to get it right? Let's go do it again.
Lefty! Why?
Get back in there!
After 384 tries, this primitive being is reflecting upon itself.
And now for the explanation of the second part. The force that we applied to the weight was delivered over a longer period of time, causing a much greater acceleration. The acceleration can be modeled by the formula F is equal to ma, where the acceleration multiplied times the mass of the object can equal a much greater force. And this force added to the weight of the object resulted in much more tension in the upper string, causing it to tear before the other string could, causing the weight to come crashing down.
That is correct.
Yes!